Morning all, thanks for joining the Incentive Beta Phase Show and Tell webinar as we look to close out the project. We'll be taking you through some of the outcomes that we've learned throughout the beta phase. What we'll do is we'll have around 30 minutes, 35 minutes of the presentation, and then follow that up with 20 minutes to run through Q&As. The webinar does have a Q&A function, so feel free as we're going through the slide deck and the presentation to populate any questions there, and then we can run through those towards the end. Alex, I think you might be able to just pop or start the Q&As if it's not already live, and then we can start populating it. So just to introduce myself, my name's Adnan Mahmood. I am an Innovation Delivery Project Manager here at SSEN Transmission. I've been leading the CIF Incentive Beta project on behalf of SSEN Transmission as the lead partner. Now, just a little bit of background on the project. So, as many of us may know, energy contained in generators at power stations and other industrial facilities provides inertia as they rotate through the same frequency as the electricity grid, providing stability to the system. But as we're increasingly moving to more sources of renewable energy generation, the inertia in the GB network is falling. So the incentive project investigated how offshore wind farms can provide inertia to the onshore networks through a range of solutions located at the onshore substations of said wind farms. So we investigated 4 solutions throughout the course of the project through discovery, alpha and beta phase. So that's battery energy storage systems, STATCOMs, synchronous condensers, and HVDC terminals. Now, just to give you the overarching story, now Incentive has been through all phases of CIF round 1. So in the discovery phase, we identified the 4 solutions. And in the alpha phase, we reviewed the commercial and technical feasibility of these solutions, increasing the number of potential sub-options within them to 9, and also highlighted compelling arguments in terms of technical and economic feasibility for the majority of these incentive solutions. In particular, it highlighted that BESS, STATCOM, and SYNCON could provide significantly cheaper inertia than the current sources, and these are the options that we took forward into the beta phase and which should be investigated. Now, the incentive project had quite I call it an extensive consortium with quite a lot of stakeholders involved throughout the sector. The project was led by 4 project partners, SSEN Transmission, NESO, University of Strathclyde and the Carbon Trust. And sitting underneath them or through those project partners, we had the overall delivery team, the HVDC Centre, who are a subsidiary of SSEN Transmission, Fraser Nash, who are a subcontractor through SSEN Transmission as well, the University of Strathclyde and Carbon Trust. So these 4 organisations did the majority of the delivery for the project, and that's who you'll be hearing from throughout today. Underneath them, or in conjunction with them, you had the advisory panel, which consisted of 5 OEM or technology providers and 3 project champions who offered their development projects as case studies to the project. And you also see on the right-hand side there, through the Carbon Trust, we had access to the Offshore Wind Association partners who provided some value input to the project and also took learnings from it as well. So overall, we engaged with 11 onshore wind developers, 5 OEMs and 2 regulated license holders, which is quite a large number for a project that only lasted a year. Now, the project consisted of 5 core work packages, and a 6th work package was added on to ensure we were able to disseminate successfully and close out the project as well. What you hear through the slides today are the 3 work packages highlighted in blue there. So you hear about the regulatory assessment, the commercial assessment, and the technical assessment. So what I'll do is hand over to George who will take you through the regulatory assessment.
Thank you, Adnan. Just taking control of the slides. Good morning, everyone. My name is George Miles van der Gaag. I'm a Senior Manager at the Carbon Trust, and I was working on this regulatory assessment as part of the incentive-based project, which is fundamentally looking at the business models for our different technology approaches that Adnan outlined. Our main goal was to devise site-specific business models for these incentive solutions. We should need to navigate what we know is a highly regulated sector. The aim was to use these business models to inform the cost-benefit analysis, which was led by Fraser Nash, and both of those elements are important parts of a developer's final investment decision. Understanding the regulatory requirements was crucial for implementing these business models. We were also looking to generalize the models into broadly applicable set of recommendations, which was a big part of what we did. Our work quickly identified that there were limited regulatory barriers to the business model for BESS with uprated converters, which was good news. But we did identify that there were significant uncertainties for the business model of the incentive STATCOM, as we call it. So that became the main focus of this work package. To attempt to develop the business model for the incentive STATCOM, we developed some specific research questions that you can see here. These questions cover topics such as the ownership of the STATCOM, revenue generation, grid compliance, investment risk, physical constraints, and regulatory changes. Perhaps to draw out a couple of critical questions that we spent a lot of time on. Understanding the implications of ownership and operation under a generation license was a key question. The questions around route to market and revenue generation, particularly in the stability market and for reactor power services, were also really important, and we spent a lot of time on those. Understanding these factors was essential for developing these business models, as it covered the kind of full spectrum of considerations for what goes into a business model for the incentive STATCOM. Of course, you can't do any of this without extensive stakeholder engagement, and there was extensive stakeholder engagement as part of this work, which is critical, as we all know. We worked with wind farm developers to understand their commercial rationale and viability for incentive solutions, particularly the incentive STATCOM. We worked very closely with Ofgem, who were particularly important, and we really appreciated their time and efforts throughout the project in shaping this. But we also collaborated with DESNZ, now NESO, and OEMs, which was essential to align our solutions with long-term policy, energy security, and market requirements. Broadly, there were two options for ownership of the incentive STATCOM, but both presented challenges. The status quo is that the STATCOM is divested to the the offshore transmission owner. The other option is that the developer retains ownership of that incentive STATCOM. If the OFTO was to retain ownership, there's currently no access to the stability market for TOs or OFTOs due to regulatory conditions. And OFTOs often lack the technical expertise to optimize assets in a live market environment, which is important for the stability market. Ofgem's regime cost minimization approach also doesn't necessarily incentivize developers to design and commission incentive STATCOMs, as there is an additional marginal cost to do this, which is significant. But if the developer was to retain ownership, so looking at the second half of that slide, this would set a new precedent, as typically normally STATCOMs are divested to the OFTO. And there could also be compliance issues, as the OFTO uses a STATCOM to meet its reactive compensation requirements. So we identified a range of problems with either the ownership being maintained by the OFTO or retaining ownership from the developer's perspective that we had to explore further. To attempt to tackle some of those challenges, we developed a long list of business models that you can see here, split between developer ownership and OFTO ownership. And we were able to prioritize three that we thought were most likely to be viable options that we took forward for further analysis. Two were where the developer retains ownership, and one where the OFTO retains ownership. We ultimately prioritised option 2B, which involved the transfer of responsibilities for dynamic reactive compensation at the transmission interface point from the OFTO to the developer. This option also included removing the OFTO's STC obligations and adding generator responsibilities via alterations to the wind farm's TOCA documents, which I'll come back to shortly. But the overall approach, we thought, the reason we prioritised this is it created a much more predictable and stable environment for grid development and incentivised the developer to build the incentive StatCom in the first place. To create a clear route to market for this option, for that preferred regulatory model, the team worked with Ofgem and ESO to define what those detail requirements would actually look like. First would require the removal of the OFTO's STC requirement for reactive power compensation. So that although there was already a precedent for this from the NESO Pathfinder project mentioned there. The second was the additional generator responsibilities would need to be reflected in their contractual arrangements. So namely that TOCA document, which is a transmission owner connection agreement. So there was work to do to understand what that would mean in mirroring that obligation from the STC through the TOCA for the developer. To do this, we're kind of forward looking here, but we worked with Ofgem to create a clear process for developers to be able to do this for incentive StatComs in the future. So it would require the developer contacting Ofgem ahead of their final investment decision. Ofgem would then assess the application, run a consultation with affected SCC parties, and make a minded to decision. The Ofgem-led tendering process would help inform potential OFTO bidders about the asset to be divested and the responsibilities of the OFTO versus the generator or the developer. The purpose of creating a process like this was really important in ensuring kind of transparency of that regulatory route and to give Ofgem an informed kind of decision-making process for all parties involved. So to summarise, it was a really interesting and novel project for us. We really appreciated the support from Ofgem and others in creating that regulatory route and a clear business model for developer ownership of the incentive StatCom. We have a summary statement here from Victoria from Ofgem, who was crucial in pulling this together and creating kind of a clear route for market for this option. Just to note, Ofgem's Innovation Hub is also available to support companies exploring incentive business models further if they wish to do so. But thank you for listening. I'll now pass to Stephen Fletcher from Fraser Nash, who will take you through the CBA element of this work package.
Thank you, George. So I'm Stephen Fletcher from Fraser Nash Consultancy, and we led the cost-benefit analysis work within this project. So within the CBA, we kind of assume that you can develop the incentive device, and we kind of aim to work out whether we kind of should from a benefits perspective. We looked at this in kind of three main levels. First, from a sort of purely economic perspective, could the incremental investment in these technologies provide more cost-effective inertia than the current market? From the kind of owner-operator's perspective, can developers make a return from this, including some of the business model considerations that George just presented? And from the consumer perspective, where we assess whether for a developer to make money and provide a service, whether the consumer would actually see a benefit in reduced bills at the end of the day. As Adnan mentioned, this project's been running through several phases. Since the alpha phase, we have managed to mature the CBA in various ways. So it's kind of evolved with things like the ownership models that George described. So we were able to assess those and understand the implications of different ownership arrangements on the kind of business case for developers. We're able to engage OEMs and developers in much more detail to give us a fuller picture of the cost and what they were looking for some of these devices. And the stability market has sort of moved on over the sort of course of the project as well, so we were able to incorporate some updates and changes to the sort of the picture from that perspective. So what did we find as part of the CBA work? It's probably worth first stating that for the economic analysis, and for both technologies, we're looking at the kind of incremental cost increase of adding stability or inertia capability to the STATCOM and the battery system. So for the STATCOM, that is kind of adding supercapacitor storage, and for the battery, that is a kind of incremental investment in added additional converter capacity. From an economic perspective, we found that both the STATCOM and the BASE options could reduce inertia costs compared to the existing market. We did see that the STATCOM cost and hence the kind of required price to achieve a return, or inertia price to achieve a return, is higher than the battery, but we can recognise that some of these costs are kind of first of a kind for the STATCOM technology, and we would expect them to come down over time. From the developer's perspective, that's where it gets a bit more complicated for the STATCOM options for some of the reasons discussed earlier on. So as a developer, we assume you have the kind of opportunity to receive revenue for inertia, reactive power, and would have lower TIN-UOS charges as part of your connection. But as you no longer divest what you originally would have with the original STATCOM, you incur the kind of ownership cost of these and additional costs associated with that around sort of maintenance and financing of new assets. The contract periods are another big variable here. The previous Stability Pathfinder contracts have been around 10 years. And getting a return in 10 years for both of these assets does tend to push up the required inertia price that you would have to charge to get an effective return. For the STATCOM system, we found this still beats some of the more expensive providers of inertia through previous tenders for Stability Pathfinder, but it can be sort of higher than average. We don't have the same ownership concerns for base systems, and the sort of prices here are kind of aligned with some of the previous analysis in the last slide. From the consumer perspective, so there is an opportunity to reduce inertia cost still with using the STATCOM option, but we noted that this may be balanced out by reactive power payments to developers. This is quite a large variable as part of the work and is really dependent on location and various other kind of system factors which can tip the balance of the CBA. For the base system, based on the inertia prices that we modelled, we found that sort of balancing costs should reduce and consequently consumer costs should come down. There are two other kind of areas we looked at as part of this project. One was on system strength and one was the interaction with CFD pricing. On strength, we found that we kind of looked at a scenario where a wind farm needed a stability asset to increase system strength at the point of connection. We found that if that's all you need to do, then a synchronous condenser is probably the most cost-effective option. However, if you can also sell inertia from your stability asset, the incentive STATCOM provides the highest return and provides a good option in this case. On the CFD side, I guess in theory, we're saying if a developer could make a return from a stability asset, they could decide to reduce their CFD price in order to become more competitive. But in reality, we found that it would be very difficult to align sort of timing on CFD bids and stability market bids to support this kind of idea, and it would also increase developer risk. So just kind of in summary, in terms of what the CBA kind of outputs provided, we still have a good positive economic case for both of these technologies. But currently some of the market arrangements and realities make the case for the STATCOM more complex at the moment. The battery system looks compelling across the board, but it must also kind of be underpinned by revenue from other markets. So we've only assessed the incremental cost of providing stability from the base, there are other markets that would sort of make its return elsewhere. But as discussed in the last slide, the StatCom does kind of fare well when viewed from a system strength and inertia perspective. Some future considerations. On storage duration, the cost of the StatCom system is fairly sensitive to required storage duration, how many seconds of inertia provision you require. There is work ongoing to kind of understand what this level needs to be, and if the duration can decrease, this solution could become more cost competitive. And on the system strength side, strength currently kind of measured by short circuit contribution. And other projects are kind of assessing this metric and looking at alternative approaches for this. If our alternative measures of system strength are adopted, this could make the commercial case for grid forming technology more compelling. Another couple of points just to note, future stability markets, that new markets are being launched at through time. So we've used the stability pathfinder of reference. This was the first of a kind and sort of dominated by synchronous condenser technology. We will see how the future markets play out, and that will inform the future competitiveness of these technologies. And finally, on this technology maturity, the StatCom in particular was a first of a kind technology. We would expect these kind of costs to decrease over time and impact the competitiveness of the technology. As all slides from the CBA work, I'll now pass over to colleagues from Work Package 3.
Thanks, Stephen. Hi, everyone. My name is Sean Tian, an engineer working at the HVDC Center, part of SSENT Transmission. And I'm working together with Dr. Adam Disco from University of Strathclyde, working together for this work package, to investigate, this type of devices from technical sides. So what's our objective? So firstly, we want to understand the incentive device, how it performs. This device can make the grid code requirement, and we also want to share our suggestion on the Y-strip after our testing, what can be made better for the future grid code requirement. And also, of course, our proposal is using this kind of device working with offshore wind farms. We surely want to know what's the interaction between these two devices. This is our another objectives. So in the beta phase, what we want to testing compared to the previous phase, we want to testing this device provided by Venter in their black box formatting and using their control structure, and also working with some the offshore wind farm with the set certificate data. So a lot of tests go to us. The first test, we need to set up our testing environments, and also second one, we need testing stand alone the performance. When we stand alone connect the incentive device to their AC grid, what is the performance. And the third test is to test it with the offshore wind farms. And as George mentioned earlier, the engagement and the distribution is very important for us because we need to know what the kind of service can provide by OEMs and what's the wish list from offshore developers. And also the distribution, we want to share the funding and the suggestion from this project. So this slide is showing our test bench. You can see, what the test bench looks like. So all the testing is running at the offline piece card environment, and the offshore wind farm is functioning in grid flowing mode with the transmission solution. It can be a HVAC and also can be HVDC. So incentive devices function grid forming mode and connect together at the onshore substation. The AC grid in this project, we're just using the controllable ideal AC source. It can control by different ICR value. And offshore wind farm, all the model we're using the generic type from the public, and also but incentive device we're using the Venter types, battery and the grid forming StatCom with energy storage. Testing events is focusing on the frequency, faults, and angle, and also we did the frequency scan for our proposal. So talking about the offshore wind farm model, they just mainly is for the offshore with HVAC and offshore which is HVDC. So for HVAC type of offshore wind farm, we're using the type 4 wind turbine with scaling transformer. And onshore, their HVDC, we're just using their HVDC MMC converter as their onshore MMC converter to represent their whole the HVDC link. So all the model can found in the public, and their HVDC, their wind turbine model came from their PISCA library, and their MMC converter is from their HVDC open source model. And also we got the help from the project champions with their input. We made our model close to the real life, and also we aid the power and frequency droop control with the deadband to represent their limited frequency sensitive mode. So incentive device, again, all the black box model. This is why you see the very black box on the slide. So we cannot see any, the control design, protection design from the model because they are all black box blended to us. But we received the two grid-forming STATCOM model with the energy storage system, and also two grid-forming battery model from the OEMs. So just want to be clear here. Our work package is not examine their control structure. We just examine what's their vendor's design. We are not in their area comparison different grid-forming topology. So here is our simplified test grid. You can you can control it by the SCR value to represent different system strength, and also you can control about different testing events. So we're talking a lot about the testing event, the testing plan. What is test plan came from? So this came from the GB grid-forming Patek guidebook. It's published by NISO in April 2023. So mainly two-part, and the grid code company testing, and also the small single scan. And I will spend the time in the floating slide to explain what the test we did. So grid code, the company test is mainly the frequency, fault, and angle jump. And small signal scan, we using the two scanning tool, one called the network frequency propagation scan tool, and another one is impedance scan. So I put the link on the slide that you can easily to access this guidebook. So help yourself. This slide showing the testing event for the frequency. So in total, we have 9 testing cases. So from testing 1 to 4, you can see just simulate the ramping event from 50 to 52 Hertz or 50 down to the 47 Hertz using different roll-off value. And also frequency 5, we want to examine how is performance when you're fixing the frequency step. So this is our testing 5. You can see the red color highlighted in the even 6 and the even 7 because they have a 5-second run up, a run down event. I will discuss it in detail in the next slide. So last 2 slides, just to be clear, is not from the guidebook because during the testing, the NISO published their midterm the stability markets, and we found this testing in this book. So basically, it's just repeat the frequency events. So we just put it on our test list. So back to this 5-second testing events. So after our testing, we may want to, suggesting something, maybe we can removing or relaxing this 5-second ramp event because they can help us minimize the unnecessary hardware requirements, especially, for the grid-forming STATCOM with energy storage. If you want to provide inertia, you need your energy storage system behind your device. And that will be cost, the money to build up your energy storage system. If we want to make this 5-second run-up event, we may need more, the hardware. So they cost the investment money, and it's kind of boundary to stop the decision maker or interest stakeholder to, give up this option. So our one of job is want to bring this technique to the market as soon as possible. So we may think about it in another way. If we're asking grid-forming STATCOM to provide voltage and frequency support in 1 second, the green area is the energy you need. If you surface for 5 seconds, the blue area is you had to use. So we can ask the grid-forming stop the provide inertia at the red dot because in the real power system, you including the grid-forming device and grid-falling device. After red dot, after 1 second, your risk of grid-falling devices in the system can provide a dynamic response. So they can help us to reduce this boundary. So this is our thinking or suggestion. We need further discussion with the different parties to find the better way, but this is just our current suggestion. Apart from frequency event, it's just a very normal. It's not normal, but very useful. The testing event for fault and angle. Where for the fault event, we start simulating different types of fault to examine what their performance from their incentive device. And also the angle change is a 5 degree and 60 degree jump at the grid intercut for the 0.5 seconds. So move to the next slide is discussing the small signal frequency scan. The first tool we're using is called the network frequency propagation scan. This is also recommended by the guidebook. So you just use them to examine the device the response to the small signal. We're injecting the small signal to the device and at the independent frequency, and we measurement active power response. And for each of the independent frequency components, we use FFT to see what is performance and to generating the plot. And you can use the following equation to get your equivalence inertia and damping factor. So this is the good tool to start with, can give you, the inertia constant and the damping factor of your device. So, one job for our engineer is quantify their system, quantify their factor and help us to analyze it. So another small signal scanning tool we are using is our HVD center in-house tool to the measurement their impedance at the frequency domain. Similar to NFP tools, we just injecting the propagation voltage to the system and measuring the current using the FFT to calculate the impedance at the independent the frequency, the component, and this is the multi-input and multi-output modified sequence domain impedance. And we can use the further analyze using Nyquist plot and both plots to analyze the stability, the device, the stability and find the interaction. So we have another webinar hosted by our HVD Center to discuss the small signal analysis method in deep. So here's the link. If you're interested, you can go there and watch with it. I'm sure that will be very interesting to talk you. So go to the conclusion. What we did, we're testing this incentive solution and again, including their standalone performance and also with the offshore wind farms. We're testing the 4 grid forming devices in total, and this thanks for the OEM involved, our advisory panel. And some of the devices is first to be tested by third party, like the incentive project. And also we need to show the the respect to the offshore developers, project champions. They give us their input to make sure our offshore wind farm, the generic wind farm, close to the real world. And from the testing, we investigate and see the performance, incentives, STARCON, and the battery both can provide stability support to the system. And but as I mentioned earlier, from the grid code testing, we may see some potential changes to the future. And that's 5 seconds ramp up and ramp down even maybe can be relaxing, because if you think about in another way around, if you are the onshore substation owner, you want to upgrade your STARCON in the future, and you also need to think about your space for hosting the energy storage and this hardware. So definitely need more discussion here. We are keep to engage with different parties to see the best way. And from a small signal the scan analyze, we see some of the even advance to this kind of type of device can improve the system strength, but it's not our incentive, the main project, the main objective. This is the need for the examination, because on at the academia and the market, they have a lot of the methods to examine their system strange with their converter domain system. So we need a further examination. So they can be our next step. So apart from this webinar, we did another webinar to just focusing on their testing, their technical side, and also we submit our academic paper abstract to the IET ACDC conference. So this morning we received the news that this abstract has been accepted by the ACDC conference. We will prepare the full paper, and we will show more detail in our academia paper. And both the HVD Center and Adam, we both join this grid forming the expert group to share our funding from our testing. And also, we also want to learn what's their, another expert in the JB or in the world, what's their, contribution to this grid forming devices. So a lot of discussion will be going on, and we will keep as the incentive party in, various groups to share our funding. So that is everything from our work package 3. So I hand over to Kia for the next.
Hi, so I'm Kira and I work in the offshore wind team at the Carbon Trust, and I'll keep this section fairly brief in the interest of time. So as discussed, the main conclusion that can be drawn from the incentive beta phase project is that offshore wind is well placed to be able to provide this cheap and necessary inertia to the onshore grid with the addition of these incentive solutions. The UK's 60 gigawatt by 2030 offshore wind targets means that a lot of this new build generation storage and transmission assets are currently under development. And incentive is pushing to ensure that these new build assets will include the capability to stabilise the system or to build smarter using these novel technologies that can provide that stability. The project has shown that the build better approach is a cheaper way of providing stability than building kind of standalone assets for stability services. And if the huge pipeline of new build assets are built without this capability to provide stability, then this opportunity will be lost. The assets being built today will be in operation till around 2050 or 2070. And we're working in a closing window of opportunity to build these better solutions. We are seeking to accelerate the uptake of these novel technologies to provide stability to seize the opportunity while the window does remain open. But this is a step change in capability and philosophy for the renewable generation and transmission businesses. It's going to require collaboration and support to uptake these is kind of the key takeaway, really. There is a follow-on offshore wind accelerator project. So out of the incentive beta phase project, we are developing a scope for a smaller next phase project, which will aim to provide an evidence-based guidance document for offshore wind developers on how to specify, install and operate incentive solutions, particularly the incentive STATCOM solution. And this will enable offshore wind developers to uptake these technologies and will provide them with clear guidance on how to implement these in the UK market. The next phase of the project will achieve this through 3 main pillars. The first of which is leveraging German TSOs progress. So the German TSOs are installing these grid forming or e-STATCOMs in 2025 and are ahead of offshore wind in general. Therefore, we're designing this project which will be able to share learnings and testing results with the German TSOs to learn more about the use of these devices. The next pillar is inertia provision from a complementary resource. So one of the outcomes of the incentive beta phase project was the postulation that stability assets at an onshore substation and an offshore wind farm can provide more inertia response than a standalone stability asset elsewhere on this system. This hypothesis suggested that the incentive solution provides inertia for a short time before the offshore wind farm takes over with a dynamic fast frequency response. This question was discussed in the beta phases, but not examined in detail, and it could greatly decrease the cost of providing inertia and therefore greatly improve the business case. And finally, strengthening the weak grid connections for offshore wind. This section of the project will look to examine how these grid forming and e-STATCOMs can strengthen the grid connection of offshore wind farms using these incentive devices versus using kind of a more expensive synchronous condenser. The question again was discussed but not examined in detail in previous phases, and it could increase power exports and therefore revenues at a lower cost than using synchronous condensers for these use cases. The project will look to start in 2025 and will be funded through the Carbon Trust's flagship collaborative research and development and deployment programme, the Offshore Wind Accelerator. And finally, just once again to highlight the fantastic consortium that we've had on this project. Thank you very much to all the organisations we can see on this slide for all of your hard work, input and collaboration throughout the project. And also thank you to all of you who have dialed into this webinar for listening. I think we're going to move on to a Q&A session now.
Yeah, thank you to all the presenters and thanks for everybody for joining. To facilitate the Q&A, there's not been too many Q&As come through the Q&A function itself. The chat function is now open if you want to populate that with any questions, or alternatively, if you want to raise your virtual hand, and then we can bring you on mic to ask any questions as well. So yeah, any questions? We do have a question from Camille here. So upon beta closure, what do you think worked well and what you have done differently, especially when looking back at scoping the different phases? I guess in terms of working well, with so many stakeholders involved, as you can see, the number of logos you can see there, and the facilitation through the Carbon Trust. So I've got to hats off to the Carbon Trust to be able to facilitate quite a large number of organisations into quarterly review meetings or weekly meetings with some of the partners as well. I think that worked quite well with the number of organisations we've got, the number of consortiums within consortiums that we've built, and getting that input and feedback back and forth in a sort of meaningful discussion to be able to get to this point has worked really well for a project of this type.
If I'm okay to just jump on the back of that as well, I think one of the things that has been achieved quite well through this project is having the OEMs or this advisory panel kind of structure where we're able to ask direct questions about the technologies as well. I don't think that's something that necessarily all projects are able to do, and not that everyone is able to provide that input that they would probably like to for different internal reasons. And it's meant that there's been a lot of open communication between OEMs, developers, those kind of networks who are also involved, but also regulators to really hash out some of those bigger questions. And that can only be provided through having this whole system view that the project has really aimed for. And as I've mentioned, all the fantastic input from everyone on screen there. So I do think that wide consortium is probably the main selling point of this project and the main learning as well. I don't think we would have achieved any of this without everyone who's on screen.
Thanks, Kira. Another question. As the stability market changes, will any of the research be revisited or reviewed with a new business case? So perhaps, George, is that one you could answer?
It is. So I think the one we couldn't answer was the T-4 stability market, which I think is still being, as in the conditions of which are still being finalised. So most of our research focused on the T-1 stability market and access to that. But yeah, I'm sure that could be updated as more details of the T-4 become available.
Yeah, I think maybe just to add to that, throughout this project, there was a lot of moving parts, both in the sort of technical specifications for the stability markets and the tender responses to stability pathfinders and the new stability market as well. So we're both going to see the cost of the equipment changing, the maturity changing of things like the StatCom with energy storage. Plus, you can kind of see what the competitive technologies are through new tenders and markets as well. So I think we will need to keep evolving that thinking to understand and kind of keep up with changes to the market.
Thanks both. There are just double checking. There are no questions in the chat, and there's no other questions within the Q&A. If there are any further questions, feel free to raise your virtual hand, and we can answer anything else. We do. Harith Dorat from NISO.
Hello, good morning. Firstly, thank you for that. I was just interested because you mentioned stability markets. So I'm part of the what is now called the network services team, what was called Pathfinder. So I was interested in what your thoughts were about the various stability markets. Maybe a question for Stephen about the CBA, about it mentions ARPs as kind of a revenue source. I don't know whether you're kind of aware or considered any changes to that payment mechanism for reactive power. Kind of something that's being considered or touted about. So I don't know whether it's something you'd either had considered in the CBA or might consider going forward.
So aware that you are considering some changes to ARPs. We weren't looking at that as part of our work. One of the challenges for us was just to try and work out a kind of volume for reactive power that you might see for lots of the different locations, because locational variation on reactive power requirements changes the sort of the business case there. So that's kind of really what we were looking at, was the volumes of reactive power, how that might be compensated through the current ARPS arrangements, and clearly if they were to change, that would impact what we calculated in our current CBA.
Thank you.
One in the chat. So from Jian-san at NISO, roughly how long could the supercapacitor for incentive devices support inertia according to our investigation? I'm not sure this was one for Stephen or Sean.
Yeah, I think, well, for me, the answer is it depends how long you want it to. If you convert a normal STATCOM to a STATCOM with energy storage, kind of OEM guidance was the sort of minimum you would get would be around 1 second worth of storage. So as you can incorporate supercapacitors into that device, it would give you a second worth of storage there. But that can then be added to as you could add more storage there. So we're looking at devices up to, I would say, 5 seconds worth of energy storage within that device. So yeah, you can kind of convert it. You add some supercapacitors. That gives you a second. They can then sort of build up additional storage capacity there to, not quite give you as much as you want, but into multiple seconds.
Thanks, Steve. Okay, there's no more questions, so I think we can close it there for today. I have posted a link within the chat function to the ENA network portal for the incentive beta phase. Under the documents tab, you'll find the publicly available summary reports. A version of the slides will also be made available there as well, and a recording of today's session will be made available too. So yeah, thanks all for joining and listening to what we've managed to do through the project so far. I guess hats off to all the presenters and the wider delivery team for all the hard work they've done over the last year or so. And also, again, for all the logos you can see in all the organisations that have been involved. It's been very much appreciated. And to everybody here, thanks for listening. I guess we can now all disappear and get some lunch.